This is the third lecture of the chapter of scattering, or you can say this is the first lecture for 3D scattering. So the plan is following as written in the page. We'll first discuss about setting up of the problem, which means what are the relevant quantities we want to calculate. And in analogy to the 1D problem which we studied in the great detail, you will see basically we'll do the same thing, but just because it is 3D, things will change a bit. That's the only difference. And we'll set up the problem as a problem of time independent Schrodinger equation. We'll make some answers and assumptions, and that is a simplified way of approaching this problem. And this is along the line of the textbooks, of most textbooks. And for you I will suggest Griffith, but any textbook follow this, most textbook follow this line. So after we set up the problem, we will discuss three uh, techniques of this kind of solving that problem, or three what will I say, like the tools of the trade for this problem. And these are like partial waves, S wave scattering, and Born approximation. I will not necessarily do them in this order. It could be I might start with the Green's function solution and Born approximation first, then go to partial wave and S wave. But just this is the list of the topics. So that roughly constitutes a typical master's level scattering course. But if we want to go a little deep into the subject, which is actually I think it's useful to go there, we we can go to this part where we set up this scattering theory from a framework of time dependent perturbation theory and use the Lippmann-Schwinger formalism, which is very generic, and then we'll take the limiting cases to get the approximation which we already used as a starting approximation for this part, for this part where we do S wave, partial wave and Born scattering. So depending on the time and how much progress we make, I will keep this final part of formal setup of scattering theory. Okay, so with that plan, let's remind ourselves that what we did in 1D. If you remember, in 1D problems, we set up the problem as a problem of where we discuss this S matrix and T matrix formalism, and we describe everything in terms of reflection and transmission. And that is indeed the only two possibilities in 1D. In 1D line, if you encounter a hindrance on your way, you have only two things you can do, either pass through it or reflect back. And that is what we describe. And we use the language of S matrix and T matrix to formalize it and calculate the necessary things very simply, like whether it will be a bound state or scattering state and all that. And notice these are all essentially two body problems, at least two body problems, even though we are solving it in the framework of one body plus a potential. But the cause of the potential can be thought of as a second body. Like for example, when we did this central force in last semester, we had a a nucleus of an atom which is generating a charge, and then there is another electron which is rotating around that nucleus. Now we treat this problem as a particle in a central field, which is Coulomb field. But this Coulomb field, the reason of the Coulomb field is another particle which we don't take into account. So essentially we reduce down a two body problem within some approximation, and that approximation is when the mass of the generator of the field is much higher than the particle which is rotating around it, like the electron and nucleus, then this approximation is a valid approximation because that mass is almost immobile. That is basically our Born-Oppenheimer approximation. But if that masses are comparable, then that approximation is not valid. So in this course we are mainly focusing on single particle quantum mechanics, so we will discuss things from that framework, which is one particle interacting with a potential. So that will be our approach throughout. So now that you understood that or realize that in 1D there are only two options, one is reflection and another is transmission. In 3D there are many options, like particle can go in arbitrary angle depending on the incident angle, the reflecting angle, and the transmission angles, and these things are not so simple or binary because there are many places and many directions to go. So we need a different characterization. Instead of a say reflection and transmission, we need a different thing to describe that. So we will build up that thing first. So what is that thing? That thing happens to be the cross section. Now cross section is intuitively, you can understand, it is very easy to figure out. So if you throw an object towards another object, now it will depend on how big the object is where you are throwing at, and the cross section of the object intuitively will decide what is going to happen to the, classically, if you think classically, what is going to happen to that scattering process. Like if you throw a ball towards another ball, like if you are throwing a ping pong ball towards a football, versus if you are throwing a ping pong ball towards a cricket ball. So depending on if it is a football, then it's, if you throw it at the middle of the ball, it is likely to reflect. If you throw it at the edge of the ball, then it is likely to scatter at a different angle. And in a cricket ball same thing will happen, but since the radius of the cricket ball is much smaller, this phenomena and the probability associated with that reflection transmission will vary a lot. So naively speaking, this cross section is that takes into account of that. But there is also another factor, that when you are throwing it, and how much angle you are allowed to vary. Like for a cricket ball, for example, a scattering angle on which the projectile you are throwing versus the football at which angle you are throwing, so that also comes in picture. So it is not just the size of the object, big depending on the size of the object, how you are throwing it. So all these factors comes into a description of a 3D scattering, and we'll learn a nice quantitative description of that, which is the cross section. So notice that in scattering there are various types of problem, although all can be discussed under the some same framework. For example, it is possible that the target is fixed but the projectile is moving, which is what happened for roughly fixed, not exactly fixed, but for example, what happens in the uh, Rutherford gold plate scattering experiment. So what he did was he showed that if you throw a beam of alpha particle on a gold plate, they will scatter, and how they will scatter, that gave him an idea to develop the theory of atoms. He showed that most of the particle will not even notice anything, because of course, so if you're throwing a ping pong ball towards a gold plate, it will always reflect or deviate, or something will happen. It is unlikely that it will pass through it. But if when you are throwing like some small particle, let's say alpha particle, they are very small, so they can pass through the empty spaces between the atoms without seeing anything, and that helped him to conclude that most of the space inside atom is empty. If it encounters an electron, then it does a very mild scattering, because electron is much lighter compared to alpha particle. But if it encounters a nucleus, then it can completely reflect back, or can scatter at a certain angle, classically thinking. So that was basically the basis of this experiment, and that helped to develop the structure of atom and all that. So that is a type of experiment where the target is fixed but the projectile is moving. Now another class of experiment is where both the target and projectile are moving at a comparable speed, which is what happened in particle colliders like LHC. So where you are accelerating two particles towards each other and they hit each other, and then that is also a type of scattering experiment. But if you think, you can also map these two problems are not very different theoretically, because you can go to the rest frame of one of these two particle and consider the other particle is coming towards it at a double speed. So these are two types of thing, and then there is Mm, Also other type where the projectile is faster than the, and there are some mild variations of these types. For example, the projectile is faster than the probe target and all that. So this kind of example keeps appearing all the time, mainly in particle physics and condensed matter. Particle physics, you can imagine the whole holy grail of particle physics is scattering experiment, where by colliding two particle you learn everything you are about to, supposed to learn about particle physics. So it is the experiment in particle, the only experiment probably in particle physics. Condensed matter, there are multiple things, but one of the most important thing is a electron traveling through a solid. What it will do, it will encounter many atoms, ions and all that, and it will keep scattering off from here and there, bump off. So it eventually, the resistivity of electron transport in a metal, which is the one of the most common problem in technology and condensed matter and everywhere, is essentially a scattering problem. So basically I can keep stretching this list forever, but what is why, I mean, wise to say that this is probably the most important practical chapter or applied chapter in the whole quantum mechanics course, which is basically the main agenda of quantum mechanics is to be able to predict various scattering phenomena, and depending on that you can test the theory and you can know, what this theory is good for. Okay, so now let's come back to this Rutherford scattering experiment, or a experiment of the type where a solid object or some target is fixed, and you throwing a beam of particle and see what are the relevant quantities you might be interested at, I mean, to characterize that kind of a scattering phenomena. So these cross marks are represents the particles on the solid. This picture had somehow broken into two pages, and it's hard to predict that the when at which point it is going to be broken into two pages. So sorry about that, but I hope it is understandable. So this is a piece of solid on which you are throwing a beam of particles. Now the beam has a density np, and the uh, I0 is the basically the intensity, and A is the area of the solid on which it is going to heat. The beam is going to heat at certain cross section area of the solid. So that is A, and T is the thickness of the solid, and D is your detector to detect the scattering. So the intensity of this beam is important in this problem, because you want to get a high intensity such that you have a good statistics. Like as I said that it's a quantum phenomena, so you need a beam of identical particles to do the statistics and probability. So you need a good density or good intensity for statistics, but the I wrote statics, sorry, it's supposed to be statistics. But it too much intensity is problematic, because then if it is too dense, then these particles will hit each other. So there is already a scattering phenomena within the incident beam before it hits the probe and target. So that makes the whole thing much more complicated. So that is one of the thing to be considered. And then there are various other factors. So a scattering experiment is of course a very sophisticated experiment which one have to carefully design such that one can predict and do everything, and the beam is collimated enough and all that, and that is why people spend like multi-billion trillion dollars to build up this kind of setups. So we will not go into all the details of that, but you will start getting a feel of how this thing works. So one of the most important quantity, as I said, is this cross section, and the cross section can be defined as the incident intensity, or can be defined as, sorry, not the incident intensity, the intensity detected at the detector D, which is Ix, divided by the flux of particle that is falling on it, which is nt I0, where nt is number of target particle it is hitting, nta, n is the density of these particles in this block, T is the thickness, A is the area, so this is the total number of particle is hitting times the intensity of the incident particle. So number of cases that is happening to be input and number of detection at output. So it's basically a ratio of output by input at a particular angle, because it has to be dependent on x, which means where this detector is located. So it's kind of a efficiency factor, and this kind of gives you a measure or a characterization of the scattering. So a strong scatterer will have a it gives you a idea about what kind of shape and structure is there. For example, if it is isotropic everywhere, don't the x doesn't matter, then you can say something about the homogeneity and isotropic character of the system and all that. So this is the class of quantity to be studied, and we will define it much more formally in few minutes. Okay, there are other examples of scattering. For example, as I told you, a electron in a metal, or spin-on, or a fractional exotic quasi-particle, or some topological qubit, anything. So they essentially, you can visualize within some approximation, they are basically something moving in a bunch of static or relatively static compared to their speed, are the static scatterer or some targets. And through a series of multiple scattering, how this particle goes from one end of the metal or the material to other end of the material is the basic problem. Now this is also another example which is of this, a beam of particle hitting another particle or another big particle or big atom. That is essentially, this problem is that only because when I say it's hitting a region, it's basically hitting a bunch of other atoms. So this Rutherford experiment showed that if it is a nucleus and this is alpha particle, some can scatter, some can return back. Also, all these experiments you have studied in solid state physics about diffraction or this X-ray diffraction, Bragg peak and all that, they are also essentially some kind of scattering phenomena, where you send some photon or electromagnetic wave, these photons get scattered by the atoms, and because these atoms are located at some periodic arrangement, there is a well defined way to characterize that how these reflected waves will have a certain phase, and how these phases will add up at some region and or will constructively interfere at some region and destructively interfere at some other region. And depending by observing that pattern, you can say a lot about the structure or arrangement of the targets or the scatterers in the solid. So that is how you detect magnetic order or crystal structure in a solid material, by doing this kind of scattering experiment, which is X-ray diffraction, neutron diffraction, and the whole class of these experiments. So in this course we will not be concerned about all these complex phenomena, but it is useful to know that these are the ones which can be connected. So here we will mainly deal with single particle scattering, that is a particle interacting with a potential. You can think of a light particle being thrown at a heavy particle which has, and as a classic example is Rutherford scattering, where a heavy nuclei have some positive charge, alpha particle with a positive charge, so they interact repulsively with Coulomb interaction. And how will the scattering happen in that problem? So that is essentially the class of problem we'll discuss. So let's come back to defining the characterization quantities in scattering. So here we throw a single particle towards a scatterer. So the phenomena will be something like this if these are reflecting particle, repulsive particle, like this Rutherford scattering experiment as I said. This particle will not be tending to come very close to this other particle, the target particle. The probe will not try to come very close to the target, but it will try to make a path which is taking it away if it is repulsive. So the important quantity is, for example, B. B is the uh, closest distance, so between where the projectile can go to the scattering center. By scattering center I mean the where the other particle is located or the other source of the other field is located. where the zero of this field, if the field is a Coulomb field, where is the zero of that B by R. So this is called the impact parameter. This thing is called the impact parameter. The other important quantity is the scattering angle, which tells you that if I to connect the asymptotic lines, like if I stretch this incoming line and stretch this outgoing line, these are the two asymptotic and incoming and outgoing trajectories, what angle do they make? So these are two of the important quantities we want to know, or we want to use to characterize the problem. As I said, because it's a 3D problem, all these factors are important. Now you can again say why it is just one number B, it could be two numbers, but that is also, there is an approximation involved in that, that it's a simplified central force. Because it's a central force, the azimuthal angle, the phi angle is not important. If it is not a central force, then you need another parameter to describe the impact parameter, or at least you need to say it like how you are going to calculate the distance. Like it could be the x-axis and y-axis square, x-axis square plus y-axis square. And the quantities of it, and as you can imagine, these quantities depend on each other. So normally theta is dependent on B, so you normally calculate theta as a function of B and the incident energy. Of course, how hard you throw or how softly you throw, that decides a lot. That we also learned in the 1D scattering. If it is too soft, there will be no scattering, we saw in 1D, and if it is no transmission, if it's too hard, it will be all transmission. So here also all these various possibilities are there. But sometimes you can also write the B as a function of theta. It's also sometimes useful for certain purposes. Okay, now we will define more quantities to give a more formal picture. So now let's say I consider that I have a uniform beam of particle of kinetic energy E is incident on a scatterer, and I define a differential quantity, because this beam I can separate it as like two annular regions between radius B and B plus dB, and this is the uh, cross section of the incident beam, which is d sigma given by B d phi dB. So now these particles will be scattered in some region of which is within this solid angle d omega, and you can compute this solid angle in terms of this angle. So this inner, again here is another annular region where the inner circle has a angle theta with the collision line, and outer circle has angle theta minus d theta. So if that is the quantity, then this d omega solid angle is sine theta d phi d theta. So the particle which are within d sigma, they will evolve to lie in the cone of solid angle d omega. So that is what we will expect, and we will define a efficiency of this by a ratio of these two quantity, which is d sigma d omega. So that is given by, in terms of these quantities, is b by sine theta db d theta. The d phi is same in both cases because we are considering central force. So see, central force is uniform in both direction. This as in all the directions, this uniform, this angle phi will not matter in this quantity because it is coming along that line on about which you are calculating this angle phi. So the phi, it will be independent of that phi. That's why you have the same d phi in both formula. And for central force, it is always true, and it's independent of the azimuthal angle. So the final quantity of your interest is this ratio in a differential sense, and this is the differential cross section. Now naively, this differential cross section doesn't make a lot of intuitive sense if you unless you have some experience with it. But we will see from this differential cross section, we will calculate a total cross section, which is totally what we understand. And as it is understandable, this is a function of the incoming momenta k and this angle theta, so that it is had to be. So what does this differential, as I said, the differential cross section doesn't make entire sense operationally, and it might not be very easy to work out experimentally. So how to connect it with something we know, we can calculate and physically feel. So that quantity is this differential cross section times the solid angle, differential solid angle. So this is basically the number of particle that is scattered within this solid angle part unit time. And this quantity is basically number of incident particle in that region per unit time. So that is essentially this quantity represents. So basically the differential cross section is nothing but the scattered flux by incident flux. So, and flux basically implies it's the number of particle per unit area per unit time. So essentially you can calculate this quantity or simply reduce this quantity of efficiency of a scattering experiment to a counting problem. When you have an incident beam with large number of particles, the quantum mechanical probability will tell you, or even if you leave the quantum mechanics, just think of classically right now, the probabilities will tell you what are the number of particles can possibly scatter in which direction, in which angle, and that you simply reduce that to a counting problem. You count the number of particles over a area over a time and take the ratio, and this will give you the efficiency of the scattering. A strong scatterer will scatter more, a weak scatterer will scatter less. So that is basically the weak scatterer in a particular direction will scatter less. Now again you can convert it into something which you understand more physically, that is basically the total cross section. So when you integrate over the solid angle, you get the total number of scattered particle, which is essentially the total cross section. And this directly connects with what you know by with your intuition, because it gives a rough estimate of what is the scattering power of the potential. So colloquially you can say it is the total area of incoming beam that is scattered. So if more area of incoming beam scattered, it's a stronger scatterer. But differential cross section of course contains more information, and you will see that how it does that. Notice this quantity is often calculated and experimentally measured, and all theoretical predictions are done in terms of these quantities always in atomic, molecular and high energy physics all the time. And there is a unit of this quantity, this cross section. It is called Barn. A Barn is 10 to the power minus 28 by 28 meter square. Okay. So now let's do some simple example to see how this all these definitions matches with what we intuitively understand as the scattering power. So let's take the simplest example within the framework of classical mechanics. Scattering by a hard sphere, which is like a billiard ball being stuck by, let's say, some probe, some marble or something. So how you describe the potential? The potential is a infinite in this region when r is less than, so here is the origin. So if r is less than some capital R, the potential is infinite inside. So that means the particle cannot penetrate this region at all. So that is equivalent to saying there is an infinite potential barrier. And each particle can come incident and reflected, be reflected like that in such case, in case of elastic scattering. So you can describe this angle as the alpha angle, and theta is the remaining angle for 180. Theta is basically 180 degree minus alpha. So you can very easily see what is the B for this problem once you know the radius of the ball. So that is basically r sine alpha. Now we want to describe it in terms of this asymptotic line between. So theta is my scattering angle. So write down in terms of theta. So it becomes r cos theta by 2. Now you can see very easily B is greater than r, there is no scattering. The marble, if I assume that the small particle or marble has no radius, it is just a point particle, then there is, you don't even see the sphere that we expect. Now we calculate the differential cross section by using the formula blindly. If I do that, I will get r square by 4. So this is the formula we use, b sine theta db d theta. We know the b expression, everything we know, just a derivative will give me r square by 4. What is that? It is not very intuitively clear to us, because differential cross section is not something holds a clear mental picture. So we calculate the total cross section, And if we calculate the total cross section, it is basically pi r square, which is basically the geometrically cross section of a sphere. So it is, if I come from a incident particle, how I will see the sphere is basically pi r. The area, the sphere will appear as a circle to me, right? From, if I'm coming from far, from the point of view of the probe particle, and the circle will have a area of pi r square, and that is indeed what we got from this machinery. So this description matches with our intuitive pictorial description of a cross section. Now more examples, you can calculate classical calculation, do some simple classical calculation which is a little bit non-trivial. Take the Rutherford scattering, for example, for Coulomb potential. You can show for that within using classical mechanics, classical electrodynamics, that Vr is equal to A by R, which is what initially Rutherford and all did, and then they realized this doesn't fit with the description if I just think it as a Coulomb potential within the, well, sorry, I made a wrong statement here. So that was not the main point of Rutherford. The Rutherford's main point was getting the structure of atom, which is a nucleus and atom with lot of empty space. So if you use this classical formula of V and calculate this quantity, you will get the d sigma dE to be this A by 4 E whole square 1 by sin to the power 4 theta by 2. So that tells you that what is the probability of when the angle of theta is like pi and all. There are some special angle where you see no scattering and all that, which is interesting to note down. Now also notice this whole picture of classical formula is not going to, this classical way of calculating. So this definition is fine. How am I defining d sigma d theta? But this particular definition assumes that it is all classical. A point particle is coming and getting deflected and all that. Now this formula and all that thing will not work. Why it will not work? Why it will not work when you have quantum mechanics? Why? Because in this formula we assume everything is like particle. So it will work as long as the de Broglie wavelength of the incident particle is much smaller than the dimension of the scattering region. Okay? And it cannot be used when the wave description, when it is entirely wave phenomena, that you need the wave picture. It is like breakdown of geometrical optics kind of, the you cannot draw a ray line and all, because the wavelength of the de Broglie, the quantum wavelength or the de Broglie matter wave wavelength of the incident particle is bigger than the scattering region. So you have to take into account the wave structure of the incoming particle. Now there is a catch into this which I want you to think a little hard, that why we know that if the momentum is high, that means the lambda is smaller. So does that mean that high energy scattering is less quantum? If that is true, then why LIC and all are spending so much money to do higher and higher energy scattering? So low energy scattering apparently seems to be more quantum. But what more can you see in high energy scattering? Think about that. Okay. So now with increasing wavelength, the quantum features gets added. Then the uncertainty comes into picture. For example, if I consider this direction as the z direction, so this is, let's say, the x direction. So this b, this width is basically my uncertainty in the x direction, and also that has an associated momentum in that direction, px. So it seems to be saying that if quantum mechanical properties are important, then you cannot know the x and px both with full certainty. That's what uncertainty principle tell you. But for a well collimated beam, this px should be 0 actually, because the entire momentum should be directed toward the scatterer, For a good quality experiment like CERN and all, the beams are very well collimated. They use the superconductor magnets to collimate the beam and all that. So that is, so you know the px to be precise, but then you cannot know the impact parameter. So this kind of picture, this kind of description cannot work. So we need to calculate all these differential cross section and everything using a quantum mechanical wave function. So that is the main thing we'll learn in this chapter, how to do that. Okay. So also one more point to note, that a scattering is phenomena is essentially a continuum unbound initial state that is transformed into another continuum unbound final state, because it is coming from infinity, as I said earlier also in the previous lecture, that when you look at a normal scattering phenomena, it means some light is falling on an object and then reflecting or transmitting to your eye. Then you can say, oh, this object what kind of properties are there in that object. Now both the incident beam are coming from far and going far from the actual object where the things happen. So they don't themselves encounter a potential at asymptotic limit. So it's the problem of a continuum unbound initial state that is transformed into a continuum outbound final state through the action of some potential for a finite time, for a short time. So that is why one can visualize this problem as some time dependent perturbation theory. Like if you see from the rest frame of the incident particle, it has no potential, no potential, no potential, then it suddenly starts feeling some potential for some time. Then again this potential reaches at a peak in a time dependent manner depending on the speed of the incident particle. Then it falls off and again it becomes gradually to no potential. So this is essentially a time dependent perturbation theory problem if you think it that way. And that is indeed what we will do in the formal description of this problem. But before that we will do a more heuristic or intuitive description in some limiting cases, and there we will not use this language of time dependent perturbation theory. So this essentially the problem becomes the Schrodinger equation for unbound eigenstates, and how we want to solve that, and the energy eigenvalues, and connect these eigenvalues and all those to the cross section and measured intensity. That is the whole game in this chapter. We already did that for 1D, and we'll now do that for 3D. Now also notice that we know that the particles in the incoming beam are best represented by a wave packet, because the particles have different momentum and energy and they are known with different precision and all. But although it is true we did all these problems in 1D scattering and earlier also, that in first semester and in quantum mechanics 1 in previous semester and this course also, as a plane wave. But we know a plane wave can be thought of as a superposition. A wave packet is a various kind of superposition of plane waves. So we know if we have solved it for a plane wave, we know how to solve it also for wave packet in principle. And we discuss those in the form of some problems which are there in the Griffiths chapter 1 or 2. So here also we will assume all the particle in the initial beam, in the incoming beam, are represented by a broad and long wave packet, which is essentially a plane wave, and that is propagating entirely in the z direction. And before they reach near the scatterer, they are represented by infinite plane waves, which is like e to the power ikz minus omega t. But post scattering, they are detected again after a long distance, where they can be described by a radially outgoing harmonic wave that is asymptotically another plane wave but a spherical wave, and the direction and the amplitude of the spherical wave depends on the direction it is moving in because of the nature of the scatterer. So we'll see how to formally, this picture is intuitive right now, but we'll work it out formally also. But this picture I hope makes sense, because that is what is. So if to make sense, let's look at this example. Think of in terms of water waves. So let's say you are sending plane water waves. At time t equal to 0, they are originated from somewhere. They are originated from far apart, because they are also essential. How can you generate them? You can generate them by vibrating some motor in a water tank. And if you are far enough from the source, it's a good enough approximation to call them plane waves, that you know. So now they are coming into some scatterer, some obstruction, some object. When it reaches that object, it creates a ripple of spherical waves if the object has this symmetry and all that. I mean, even if it doesn't exactly have the symmetry, it will create a ripple of spherical wave but the amplitude of the wave, one can think that the amplitude of the wave is dependent on the angle and it's not homogeneous and all that. Some of these waves will even return to the, will go towards the object from source and interfere with the source plane waves. So all these phenomena will happen, and that is what we want to describe, because it's an essentially a wave scattering phenomena. That is where it boils down to, and that is the whole game of quantum mechanics. Okay, so now we will describe this problem, and we want to, of course, you are have these arrows to show that this thing can have defined momentums, and this detector is placed at defined region at time t, and it will capture this plane wave and then it will make the observation. And again, when it observe, it will collapse and all these usual quantum mechanics phenomena, as you know. So that is how, that is the picture, and based on that picture we will do the calculation. Okay. Okay, as I said, this elastic scattering, the wave packet will scattered with equal energy but unequal amplitude, but and you have to also take into account the scattered wave interfere with the incoming wave, and that will tamper the incoming wave also. But we'll come back to those points later. Within some approximation, we'll think that that is not the case. Some incident wave, plane wave is coming and it is scattering in some object. Okay, so now the most important quantity to calculate in this picture, the quantum picture, is scattering amplitude. And we will show that how to connect this scattering amplitude with the differential cross section, which is what we measure in within a classical sense. We define the differential cross section as a measure of the quality or strength of scattering, and we'll connect these two quantities together. So let's set up the scattering problem as a time independent Schrodinger equation, like the way we did in 1D. We solve this, essentially this wave equation in that case. So we'll send an incoming wave with energy E propagating along z direction, which is essentially this picture. This is e to the power I k z with E is h cut square k square by 2m, and as r going to infinity, the outgoing wave is some f theta phi, some angle dependent angle dependent scattering amplitude multiplied by a spherical waveform. We know the spherical waveform is e to the power I k r by r, which we can show by solving the Schrodinger equation in the spherical coordinate, or we can also see it intuitively by saying this is the way the probabilities gets conserved, that when you increase the area by 4 pi r square, or at least order of r square. So this 1 by r will balance it off such that the probability is conserved. I mean, this is the wave function, so probability is square of that, so that is how it gets balanced. Okay, so we know this is the spherical waveform and that will have this amplitude. So this is the intuitive picture. We will also work out this form if there is time, that why, how to get it starting from without making any assumption, and then put the assumption and write it in this form. Okay, so now the Ansatz wave function is basically this psi in plus this psi out. Also note, if it is a central force, a central potential, then that is independent of the phi, will be independent of the azimuthal angle phi, as we discussed earlier. So it will be just f theta. So that is the definition of my scattering amplitude, and that is the main thing to calculate. Notice that the scattering happens at a very small region, at a very small obstruction, and that influences the outgoing asymptotic wave, which you detect far apart. So this Ansatz is an asymptotic Ansatz, which is far apart from the scattering event. So that is why it doesn't have any r dependence, and it is only dependent on this angle f theta phi. So how is it related to the differential cross section? So that is what the main point. So let's calculate for that the probability current, which is something we calculated in last semester for the 1D transmission reflection problems. And conservation of probability tells you this. So for the incoming wave, the probability current is just this h cut by mz if I plug in the e to the power ikz into it. And that is intuitively also true, because classically you can think it as a beam of particle with this velocity, which is h cut k by m, and that tells you basically the current. The current is basically now amount of mass passed in per unit time. So that's why it's a velocity. Similarly, for the outgoing current, we can also calculate the same quantity by taking the spherical coordinate derivative on f theta ikr by r, and it will be this with an 1 by r square term. And again, since we are interested about the asymptotic limit large r large z, or large r at least, because the z is also far apart origin, so this term is not very important. So this is the first non-zero term. So the j out can be written as this h cut k by mr square f theta square r plus order 1 by r square. Okay, so if that is the case, so now I can write this as a, in the r going to infinity limit, the flux of outgoing particle crossing an area dA in a solid angle can be calculated by doing this j out dot r dot dA, r cap dot r cap dA. This is the area vector, its projection on this outgoing current, and that tells you basically the flux of outgoing particle crossing an area dA in solid angle d omega, and that quantity is basically this. If I plug in all these forms and write down the dA in differential form. So the differential cross section, from here I can work it out to be the d sigma dA is f theta square by taking this appropriate ratio of j in and j out. As we discussed that the differential cross section is basically this ratio. So if we take that ratio, we get f theta square. So the scattering amplitude, in quantum mechanical language, the scattering amplitude we calculate, this factor is basically the differential cross section as we defined it in classical, within the classical framework. And that is the final quantity we want to calculate in these scattering problems. Again, we can integrate it and get the total cross section as well, and that is basically we set up the problem as a calculation of scattering amplitude and connected with our intuitive description of cross section of a scatter, which characterizes scattering phenomena. Okay,